Now in this video we're going to be discussing the diode forward voltage and the forward voltage drop. They're really the same thing, but in any case you should know by now, but even if you don't, it doesn't really matter, it's not that complicated. Diodes conduct easily in one direction. That's called forward bias. When you insert it in the circuit, based on the direction of current, will flow easily, and it blocks current in the other direction. And generally you want to keep that voltage in the range that it blocks it, except for the Zener voltage, which may also be called an avalanche voltage. Those are specially made, so when you reach their breakdown or Zener voltage, you can actually do that with the Zener or the avalanche, but you don't want to do it with any other type of diode. So in any case, we have kind of the same thing when it's forward biased, except for it's safe to pass current while it's forward biased with any diode, and it also blocks voltage, or blocks current I should say, up to a certain voltage, and it starts trickling, but at a point known as the knee voltage, then you see that the current just skyrockets out of control, basically, with just a little bit more voltage. And so what the diode does is you should have probably a resistor in series with it, and that will transfer the voltage to the resistor, the voltage above the knee voltage. So if you get to the knee voltage and then add a volt, I have a line here for 1 kilo ohm resistor and also for a 2 kilo ohm resistor. If you get a volt above the knee voltage, then you'll have about 1 milliamp of current if you're protecting the LED with the 1 kilo ohm resistor, and with a 2 kilo ohm resistor at 1 volt you'll have about half of a milliamp. So these are linear lines. It's pretty straightforward. There's a direct relationship between the current and the voltage when it comes to resistors, whereas there is not with the LED. Basically you get to a certain voltage and it just runs out of control. So now you'll notice I haven't been saying any specific voltages, and that's because the voltage is highly dependent, the knee voltage, on the diode you're using. So if it's germanium base, it's going to be around 0.3 volts for the knee voltage, and then a silicone diode, it's going to be about 0.7 volts. That's going to be the rectifier diode we're going to look at. It's in the 0.7 volt range. And then the LEDs, they have a wider range, but generally the basic LEDs that you use in circuits will be about 1.5 volts, probably a little bit higher, but in that range, 1.5, 2 volts. But diodes can go up to 4 volts, and they're not exact, but there's a range of voltages, but you're going to be about in this range with just the regular diodes you get in kits. So now, one way to get an estimate of the voltage drop you're going to get is to measure it directly with a multimeter that can do so. So this multimeter has right here, first it's a continuity tester, but when we hit select, now it's a diode tester. And so we'll do the LED first because it's a lot easier to see the LED light up when it's conducting current. And there you can see it's conducting current, and we got about 1.7 volts. That's its forward voltage. Now that was with the black probe down on the bottom pin. As you can see, it's the shorter pin. The top pin is the longer pin. So the shorter lead is the cathode, which needs to be more negative. The longer lead, the anode, needs to be more positive if you want to forward bias it. Now we're going to put the probes the other way. Going to put the black probe on top, the red probe on bottom. Now it's reverse bias. And once I get a good connection there, you'll see that we're not getting any reading. That's because there's no current flowing. The LED's not lighting up because it's reverse bias. It's blocking the voltage and thus the current that the meter is trying to provide. So now here's the rectifier diode. It's a diode just like the LED. It does not light up though, but we can still measure it the same way. There's a gray stripe right here, band, whatever you want to call it. I know you can't see it on camera, but it's there, so that lets us know that that's the cathode, the negative side of the circuit. And I don't really say this much in these videos, but there's P-type material on the anode side, N-type material on the cathode side. So that's another way to keep track of the chemistry going on. Now that I got a good connection, you can see we're in the range of 7 volts. It's actually 0.635 volts. So if we want to try to get an exact estimate of things, we'd want to go by the value that we just measured. But as we'll see later too, the amount of current flowing through diodes impacts their forward voltage drop. So now I'm going to transfer over the wires, and again, just like with the diode, now we have it reverse bias. You see that we're not getting any reading on the meter, and that's because it's not conducting. And again, the rectifier diode does not light up like the LED, so you can't see when it's conducting or not conducting. That's an easy test to see if a diode's good, is to just take a meter in diode test mode, and you can see that it lights up. You know that it's good. So now I put together this circuit that you see here. We have the resistor connected to the positive side of the power supply. It's a 220 ohm resistor. The other side of the resistor connected to the long lead of the LED. The short lead of the LED, the cathode. Long lead is the anode, this side of the LED. Cathode is connected to the negative rail. As you can see there with the jumper, it's going to the blue row. So what we're going to find when we measure voltage, we'll have close to 2 volts across the LED because of its forward voltage, and it's in that range of about 2 volts. When we measured with the meter, we saw it was about 1.7, and then we'll find there's about 3 volts across the resistor. So now zooming in, we got the meter set to measure voltage. Turn the dial there to the V and make sure there's no glare. And first we will measure the LED. So anodes on top, cathodes on bottom. And you can see we got about 1.86 volts across the LED. So almost 2 volts. As I said, that was my guess on about where we're going to end up. So now the resistor, the positive side is to the right, the negative side is to the left. We don't have to worry with this meter if we get it backwards. It'll just give us a negative voltage if we are backwards. But in any case, as you can see, now we got about 3 volts across the resistor. And ultimately, that's going to be what sets the current. So, to reinforce that, I took out the 220 ohm resistor and replaced it with a 27 kilo ohm resistor. I turned off the power. You should always turn off the power when you make adjustments to the circuit. But now we got 5 volts. Of course, with this higher resistance, the LED is not glowing very much. Not much current is passing through it. We will set the meter to measure voltage. And first we'll do the LED again. And you'll see that we got about 1.6 volts across the LED. It's not blocking as much voltage because there's less current going through it, but it's still pretty close to that 1.7, almost 2 volts that we were at before, even though the current difference is a lot bigger. We got a lot less current now than we did before. And now we will measure the resistor, and you can see that it has more voltage across it than the 220 ohm resistor did, but it's still really close. It was about 3 exactly for the 220 ohm resistor. This is a 27 kilo ohm resistor, more than 100 times its resistance, but still the voltage across it is determined by the voltage drop of the LED, even though the current difference is changing the voltage drop of the LED a little bit. It's still really close to what it was. So when you estimate the voltage that's going to be across a resistor, you just simply subtract the voltage you expect to be dropped by the diode. So now I'm not going to take the measurements in this video, but here's a circuit, or diagram fragment I should say, from another diagram I made where I did the comparison here with the 220 ohm I just showed you versus a 1 kilo ohm. And you can see with the 1 kilo ohm we actually got similar results to the 27 kilo ohm resistor. We had, with the 1 kilo ohm, I had about 3.2 volts across the resistor. As you can see, that's pretty much what I had even with the 27 kilo ohm resistor. So that's because the diode dropped about the same voltage in the range of about 1.8 from the 5 volts. So we consistently get in the range of a little more than 3 volts across the protective resistor, no matter what its resistance value. So now we're going to complicate things a little bit more. We're going to put 2 diodes in one series circuit. All these components are in series. Now I only have 1 resistor here, even though you see 2 in the schematic diagram. I only have 1. It's the 220 ohm resistor. That's why the LED is so bright. But we're going to get a similar result to what we see here. We're going to have about 1.7 volts in that range across the LED, about 0.7 volts across the diode. And then the rest of that voltage, which will be about 2.6, will be across the resistor. We're going to go over this next, this situation. But I'll leave those voltages up there so we can see them while we're taking them. We should find there's about 1.7 across the LED volts in that range. You can see it's a little bit more, about 1.8. That's still pretty close to 1.7. Now the diode here, you can see this side's connected directly to the positive rail. That's the P-type material. The anode side, cathode's over here, connects to the resistor. There's a gray band there, but I know you can't see that, so I'm not going to just say look at the band. But there we go. Once I get a good connection, you can see we're practically spot on, 0.7 volts. So, as I said before, that's going to leave about 2.6 volts left. And so positive on top. We'll move these around. You can see it's in the range at 2.6, slightly lower, but it's in that range. And so this is pretty predictable. You don't get exact values, but you do get close estimates. And ultimately, we subtract the voltages of the diodes, because that's all they're doing. They're blocking a certain amount of voltage. That leaves a voltage across the resistor. The voltage across the resistor will determine the current of the circuit. You just use Ohm's law to make that calculation. Alright, so now we have the circuit that you see here, and we added the 27 kilo ohm resistor. There you go, you can see the value there. And now we have the voltages that we should expect to see. So again, we should expect there to be about 0.7 volts across the resistor, or the diode I mean, about 1.7 in that range across the LED. They're going to drop those voltages from the circuit, so we'll have left over about 2.6. And you'll notice with the lower value resistor, this is going to be a voltage divider, so you got to look at it that way. I'm not going to go into voltage dividers too much, but resistance, or voltages are spread out across resistors based on their resistance, and other components based on their resistance. But resistors are purely resistance, so generally they're the ones you're looking at. And so the resistor with the more resistance is going to have more voltage across it, which makes sense because the current's based on the voltage across them. And so the same amount of current going through a low value resistor will have less voltage across it for the same amount of current going through a higher value resistor. That's voltage dividers. I'm not going to go into that in any more detail. I'm just going to use the meter to prove this point. So the LED is on, but we got over 27 kilo ohms of resistance. It's on pretty dim, but first we'll measure the rectifier diode. Should be in the range of about 0.7. It's lower. We're dealing with very low amount of current, so that's to be expected. When there's hardly any current going through the circuit, it lowers the voltage drop of semiconductors. And now we will take a measurement of the LED again to show that it's about 1.7 volts in that range. As you can see, it's about 1.6, so close to 1.7. Both of them are holding their voltage drops pretty steadily. So now let's do the 220 ohm resistor. Now it's not going to be exactly 0. We're going to have a number, but it's going to be very small. 0.023 volts. So not even a tenth of a volt, about a fourth of a tenth of a volt. So very small. And we should see there's about 2.6 volts across the 27 kilo ohm resistor, because it's the one. So there you go, a little more than 2.6, but considering we lost about 0.2 volts from the rectifier diode, you would expect about this range. So there you go. You can see it's very easy to estimate where the voltages are going to go. Ultimately, you get rid of the semiconductor voltage drops, and the rest of it gets spread out between the resistors, with the higher value resistors, if they're unequal values, taking the higher brunt of the voltage. In this case, this resistor is providing practically no resistance to this circuit based on this resistor's value, so the higher value resistor in this case is taking practically all the voltage across it. Alright, so now we're going to wrap this up with this circuit. First though, I want to say this is a really long video, so I'm glad you stuck around this long, but these are really important principles for every electronic circuit. Generally, you have voltage drops from semiconductors based on their PN junction passing current through them, and then generally you got multiple resistors dividing up that voltage for different reasons, and other resistances in the circuit dividing up the resistance. And so this is a very important topic to cover, voltage drop and voltage division. So we're going to skip the semiconductor testing for this, but since we got equal value resistors, we should have about equal value voltage across them, because since all, you can see it's 1.2 volts, a little less than the 1.3. Since all of these components are in series, they got the same amount of current flowing through them. And as I said multiple times, but it's very important to know that the voltage across the resistors determines the current. So since these are equal value resistors in series, they're going to have about equal value voltage across them. There you can see again 1.2 volts. So the semiconductors are passing more current than the last circuit we did, so they're going to block a little bit more, but you should be aware of that by now, so I'm not going to waste any more time taking those measurements. But in any case, if you have this down, that's really going to help you with your studies in electronics.